All right, good day, students. I'm going to kind of walk you through the first part of the next chapter. Now, as we get to thinking about what's going to take place in this next chapter, it all revolves around similar figures. Okay, so if you think about if you've ever done a scale drawing of something, or if you've ever constructed a scale model of something, or if you have like a toy car at home that you know, if you collect something like that, I've got some in my classroom. What makes those figures similar? Okay, that's what we're really going to be looking at, and there's characteristics within these images that makes them similar. So, anyways, to start off with, to understand similarity, you need to understand what a dilation is. Okay. And so when I ask the class, okay, what is a dilation, most of you would probably agree that a dilation, you've seen dilations probably at your eye doctor, right? If you get your eyes tested regularly, once a year, you usually have to have your eyes dilated. It's not a very fun experience. It's actually really weird, but that's how they look deeper into your eye. And so when you think about dilations, you know, what's one of the catchphrases or terms in sports these days? Concussions, right? A person's concussed. Well, a lot of times their pupils will dilate. And so if a doctor dilates your eyes, your pupil gets bigger. If you're concussed, your pupil will get smaller. It's constricted, okay? And so that's a good way to think of a dilation. It's an enlargement or a shrinking of an object, okay? Still the same shape, but not the same size. Okay, so as we look at this, let's just go ahead and take a look here. It says draw dilations. A dilation is a similarity transformation. Okay, so it's not a congruent transformation. It's not a form of rigid motion. It's a similarity transformation that enlarges or reduces a figure proportionally. Dilations are completed with respect to their center point as a scale factor. Okay, so there's a couple of things that I want you to know and understand. I have seen in the past where they will ask these type of questions. They'll give you two figures on the air test, and they will say, where's the center of dilation? Okay, and so all you need to do, if you look at this shape over here, this example, they've dilated this triangle ABC with respect to this point right here. And so all you have to do is trace back through each of the corresponding points, and they'll lead you to that common point. Now, a lot of you have done this in art class in years past. What's that called? Well, that's perspective drawing, right? Some of you may be doing it this year in art, where you go to a vanishing point. That vanishing point, in this case, is considered the center of dilation, okay? So, as we take a look at the first page here, let me go ahead and go down. You are going to need your compass and a straight edge to construct this first dilation here, okay? Now maybe one thing that we should put at the top of our paper is what does this term scale factor mean? Okay, scale factor. Well, the scale factor also can be used similarity ratio or the R value, okay? These are all terms that describe how much bigger or smaller the object has gotten, okay? It's the scale, all right? I think on I have a toy car back there in the back. The scale is like 1 to 16, so it's 1/16 the size of an actual car, all right? So I'm going to write this down. I'm going to write down scale factor. Okay, or we could say similarity ratio. Or we could say R value. Okay, now when we talk these, if let's say that the scale factor, similarity ratio, or R value has a number greater than 1, okay, well, what does that mean? Well, and you can write this off to the side there. What that means is that the image is increasing in size. It's gotten larger, right? Okay. So if the R value is 2, how much bigger has it gotten? Well, it's twice the size. The similarity ratio, if it's 2 to 1, well, it's gotten twice as large, okay? Knowing that if I give my similarity ratio like this, 2 to 1, that's the same as 2, okay? Or 2 over 1, all right? So again, when the similarity ratio, scale factor, or R value greater than 1, we know it's going to be increasing in size. Well, then it makes sense that if those values are less than 1, then what's it going to be? It's going to be shrinking. It's going to be getting smaller. It's decreasing in size. Okay. So if my similarity ratio is 1 to 3, okay, that's the same thing as saying 1/3. Okay, it's actually 1/3 the size of the original. Okay. If any of those numbers are 1, what do we know about the shapes? Well, they're congruent in size. Okay, that's a form of rigid motion. That would be your transformation, your reflection, or your translation. Those are all having, it's the same size, they are congruent. Okay? All right, now from there, let me scroll down and let's actually do one of these dilations here. Okay? Now you notice the R value is 2. Okay? So we should be thinking to ourselves right now, R value is 2. That means that whatever shape I'm going to form is going to be twice the size. Now, with your straight edge, you are going to want to draw, and I'll use terms artistically here. You're going to want to draw your lines from your vanishing point, okay, or the center of dilation, through each of the vertices here. So if I do that, I've got one line right there through R. You'll notice that I can't be super accurate with the computer here. You guys can be more accurate than I can on my computer, the way it's set up. But I'll draw it. It's supposed to be through C there. Okay. And I'll draw my last one through T. Okay, so I don't know in art if they call that perspective lines. I might have to draw that one just a little bit longer. Okay, all right. And if you find out that you didn't draw your lines long enough, obviously you can go back and redo those. Now, from there, I'm going to take my compass. All right, and here's the deal. If my new triangle is going to be twice the size of this one, the distance, if you see here, as it gets further and further away, okay, it gets bigger. The gap between lines gets bigger. So how much further from the center of dilation is this triangle going to have to lie if it's twice the size? Well, wouldn't it make sense it's going to have to be twice as far? Okay, so I'm going to put that on the center point there. I'm going to stretch this the given length. Okay, and you guys did this on your construction packet the other day where you measured a length, right, with your compass. I'm going to take this and I'm going to make another mark. And right there is where R prime will have to lie. Okay, that's the new point of R, twice the distance. I'm going to come back here. I'm going to do the same thing for C. Right about in there. Okay, so I come down here from point C. Now what I notice right now is I haven't went far enough with my line, so I'll have to come back and make that line a little bit further. Okay. For the last one for T, close right there. Okay, and this would be where T prime will lie. Okay, so I'm going to go over here and I'm going to extend that line just a little bit further. Okay, and that's where C prime will lie. Okay, so in the end, if we finish this up, the question that you might want to ask yourself right now is, when I think about CT, so this line right here, with respects to C prime, T prime, what should their relationship be? Well, one and the most obvious should probably be that they are twice the size. C prime, T prime is twice the size. But we also can see that these lines should be parallel. Okay, I'm just moving this down. Okay, moving this over. So these lines should look parallel if I have constructed this accurately. I see I can't be super accurate with my... I'll just put it right there. Oh. Okay, and there you go. Should be twice the size. Now, what you can do is to measure this, you can take your ruler and try to measure it, but let's see how accurate I was with this. If I come back here to, let's say, RT, and I come over here, let's see how accurate I was. There's one. There's two. Voila. That's sweet. I hadn't thought of that before. Okay. So that's how you dilate an object. Okay. So the big thing here, guys, is this. If on the air test they show you two triangles and they want to know where the center of dilation is, trace them back. A lot of times it's on a coordinate plane and you can actually count the slopes back. Okay. And you can figure out where that point's going to lie. Okay. All right. Now, I want to move to the back side, and I want to start to look at some of those coordinate plane problems that I was just pointing towards. And there's my arrow key. Okay, I'm not going to worry about this one. The big thing about this one right here, guys, is that we know that this figure, this new, it looks like a square, is going to be somewhere on the inside of this shape. Okay, it's going to be half the size of the original one. And so that's just what we would be looking for there. Okay. Now, let's take a look at the practice problems here. Okay, so it says here, dilations in the coordinate plane. To find the coordinates of an image under a dilation centered at the origin, multiply the x and y coordinates of each point of the pre-image by the scale factor, or the r, or the dilation of r. Okay? So as we think about this, they give us the original values of A, B, C. Okay, we see those there. Now this, I should point out here, if I were you, I would highlight this. This only works when it's centered at the origin. Okay? If it's centered at a different point, then you can't just multiply them, you actually have to count it. And I'll show you what I mean by that. Okay? So we have A, B, and C right here, okay, and we're going to have a scale factor of 2. So what you should be thinking right now is that it's going to be twice as large, okay. And so as they did, they took all of the x and y values and multiplied them by 2, the scale factor, okay, and that gave you the new point. Now you can test this by doing this. This is my center of dilation, okay? How far is it to C? Well, that's over 2, okay? Well, if it's twice the distance from here, it should be over 4. And we have that right there, Okay. So you can test it to make sure that works out there. If this is over 1, down 1, over 1, down 1, if I go twice as far, over 2, down 2, I've got my new point. If I go left 2 and down 2, if I go left 4 and down 4, okay, I've got my new point right there. All right. Now let's say for a moment that this wasn't at the origin. Okay, so I was going to change this. Let's say that the point was actually right here. Okay, so where would this new triangle be if it was twice as big? Well, if I'm going to go ahead and do this over 1, 2, 3, down 1, this is how I do it. I would go over twice as many and down twice as many. So this would be over 6 and down 2. This is where the new point C prime would lie. Okay. If this is over 2 and down 2, scale factor 2, so I'm going to double it, over 4 and down 4. So that's where B prime would lie. Okay. If this is left 1, down 3, I'm going to go left 2 and down 6. 1, 2, 3, 4, 5, 6. Okay. And if I draw those in, again, I'm freehand drawing this, so it's not going to be super accurate, but all right. What I hope you're seeing is that it's a similar figure. Okay, it's obviously not congruent. Okay, but it's twice the size of the original figure from that perspective. All right. So let's move down and let's take a look at a couple of things down here. What I'm going to do is I'm going to start you in on, let's say, 2 of the problems, and I'm going to see if you can finish this up for numbers. I'll do, let me look at my paper here. I will do numbers 1 and 3, and I'll see if you guys can do 2 and 4. Okay. So in numbers 1 and 3, let's start with number 1. Okay. We're going to graph this original shape. So -2, -2. There's point E. We have -2, 4. That's point F. 2, 4. There's G, and H is at 2 and -2. So what we have right now is we have a rectangle. Okay. And actually we can clarify, this is a 4 by 6 rectangle, 4 on this side, 6 on this side, 4 by 6 rectangle. And we're going to go ahead and apply the R value of 0.5. Now you should be thinking that's less than 1. So we're going to decrease the size of the shape. We're going to make it half as big. Okay? All right. So if I was to go ahead and write this out from the origin, I'm going over 2 and down 2. So if I take half of that distance over 1, down 1, there's my new point. Okay? E prime. Same thing over here, over 2, down 2, over 1, down 1. Over 2, up 4, I'm going to go over 1, up 2. Over 2, up 4, over 1, up 2. Now when we talked before, we said that this was a 4 by 6 rectangle, 4 by 6. If we think about that, if we take half as much, it should be a 2 by 4 or 2 by 3 rectangle. So 2 by 3, we see that there. So we know that we've got it half as big. You can also trace this down 2 over 1, down 2 over 1, back to the origin. Okay? We talked about making sure that we understand that it all leads back, those lines, okay, those lines all lead back from each point back to the center of dilation. Okay? Now, the scale factor or similarity ratio, we already said, is 1/2 or 1:2. Okay? It's a smaller object. Now, the perimeter ratio and the area ratio are two things that we're going to talk about later on in this chapter. Okay? Now, and I want to see something. I want to summarize something at the very end, but you may catch on sooner. The perimeter of the big rectangle, okay? Actually, since we're going from 1 to 2, we'll go small rectangle first. If I go 2 plus 3, that's 5. 2 and 3, that'd be 5 more, so 10. The perimeter of the small rectangle is 10. The perimeter of the big rectangle, 4 by 6, 4, 6, that's 20. Okay? Now what you notice, if we reduce the ratio, the perimeter ratio would be 1 to 2 or 1/2. Okay? The area ratio, if I do that, the area of this small rectangle is 2 by 3, so 2 times 3 is 6. And 4 by 6, well, that ends up being 24. 4 times 6 is 24. If we reduce that, we get 1 to 4, okay, or 1/4. So the area of this small rectangle is 1/4 the area of the bigger rectangle, okay. So keep that in mind. We're going to refer back to that in just a second here. But let's actually go ahead and take a look at the next one here. Let's see here. If I go ahead and graph this out, -2, -2, that's A. -1, 2, that's B. And C is at 2, 1. Okay. Now, we know that the R value, scale factor, similarity ratio is going to be 2, okay, or 2 to 1. 2 to 1 or 2 over 1, okay. So what I'm going to do, kind of like on the one on the front side, I'm going to take this distance from the center of dilation and double it. If I'm going up 2 over 1, I'm going to go up 4 over 2, okay. Now that's a little bit backwards from what I did before, but still the same process. Before I went left 1 up 2, so I went left 2 up 4. You still get to the same spot. Okay. This one's left or right 2 up 1, so I'm going to go right 4 up 2. And this is left 2 down 2, so I'm going to go left 4 down 4. Okay. Now again, you'd like to see that these sides are parallel. Okay, that is kind of key. Same thing with these. Okay. Likewise over here, and they should be twice the size. Now, something to think about with the perimeter ratio. This one's not nearly as easy to see what it's going to be. Okay. I didn't think about that before I started this one, but let's see here. If I go ahead and I use my Pythagorean theorem, up 1, 1, 2, 3. So we have 3 squared, that's 9, plus 1 squared, that's 1. BC is going to be the square root of 10. Okay, 3 squared plus 1 squared, and I'm going to square root that. Okay, just using the Pythagorean theorem. AB, 1, 2, 3, 4 over 1. So the 4 squared would be 16, plus 1 squared would be 1, so square root of 17. And then for AC, 1, 2, 3, 1, 2, 3, 4. We have 3 squared 9, 4 squared 16, 9 and 16 make 25, square root of 25 is 5. Okay? For the others, so if we did this right, A prime, C prime should be 2, or 20, or 10. So if I do this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. 6 squared plus 8 squared, 36 plus 64 is 100. The square root of 100 is 10. Okay. If I do AB, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So 8 squared is 64 plus 4 squared is 68, square root of 68. And then B prime, C prime, 1, 2, 1, 2, 3, 4, 5, 6. So 2 squared is 4, 6 squared is 36, 4 plus 36 is 40, square root of 40, okay? Now that looks kind of messy right there. Again, and I didn't think about doing those distances there when I first started this problem, but what I want you to see here is this. If you add up the square root of 40, okay, plus the square root of 68, plus 10, okay, you get like 24.57 and it continues on from there, okay? And if you do the same thing for the square root of 10, 17, and 5, square root of 10 plus the square root of 17 plus 5, you get like 12.2853 and it continues on. But what's interesting, if you plug all this into your calculator, okay, this is the division sign right here. Okay, make sure those parentheses are there. If you do that, and I'm just double checking my calculator here just to make sure I'm telling you correctly, square root of 68 plus 10. And I'm going to close it off. I'm going to divide by square root of 10, square root of 17, and then 5. Okay? The number you see come up on your calculator is this. You don't see the 1, but we know 2 is always over 1. Okay? So let's see here. Perimeter ratio, scale factor, R value, similarity ratio. Perimeter ratio, scale factor, R value, similarity ratio. Coincidence? I think not. Okay? Perimeter ratio is always going to be the same as the scale factor, all right, or the R value or similarity ratio. Now, the area ratio obviously is a little bit different. If you look back, ratio. If you look back on the previous problem, it's not 1 to 2, okay? So what is the relationship? Well, let's look at this one here, and I believe, let's check here, this was up 2 and over 1, 2, 3, 4, 5, 6, okay? So we have a negative 2 over 6, which would be 1/3 slope. If I do this, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. That didn't work out like I thought it was going to. I thought those were going to be perpendicular to each other. That made it a lot easier. Well, here's what it's going to be. I'll just share this with you. It'll be a lot quicker and easier. To go from here to here, a lot of you are going to think that you're going to double because you see 2 to 4. But if I double 1, it gives you 2, so that doesn't work. What's actually happening from here to here, there's a relationship. You're squaring each of these. What's the square of 1? Well, it's just 1. 1 times 1. Square of 2 is 4. So over here, the area ratio of the bigger triangle to the smaller triangle, the area it covers is actually 4 times as much. All right? And so it's 4 to 1. So if you want to jot this down, your perimeter ratio is always going to be 2 values, A to B, okay? And your area ratio will always be the square of those 2 values, okay? And maybe we should write down the similarity ratio. where does A and B come from? It comes from the similarity ratio. Okay, so if you know your similarity ratio, you know the ratio of the perimeters, and you also know the ratio of areas. Okay. Go ahead and try numbers 2 and 4 for me for tomorrow. We'll check back in and see how you did. I hope that was all understandable. If you have any questions, ask somebody else or ask myself. We'll get this figured out. Have a good night, folks.